The topic for today's lecture is rotational motion. So far we have learned the motion of linear motion. For example, a car is moving in a straight line with certain initial velocity, then final velocity, and then from there can calculate out what is the acceleration of the car if the time is given. That's a linear motion. After that, we move on to 2D motion, projectile motion. So now let's move on to another motion, call it as rotational motion. The earth is rotating about its axis. Then the car wheel is rotating. These are the example of rotational motion. Okay, let's recall back the linear motion that you have learned. Linear motion, sometimes we call it as translational motion, okay, or linear motion. So while we are learning the linear motion, we have a few terms here. Okay, what are the terms? The first term we learn is displacement, or a few parameter, important parameter. Displacement, where we use a symbol of delta s. The unit is meter. Then we have the velocity. Okay, either the initial velocity or final velocity. So we use a symbol of u. The unit is meter per second, SI unit. We have final velocity. Symbol we are using is v. Unit also meter per second. Then we have acceleration. Symbol is a. So the unit is meter per second square. So these are the few parameters that we use in linear motion. So in rotational motion, we will have this kind of parameter as well. For rotational motion, so instead of displacement, we have angular displacement. Symbol we are using is delta theta, where the unit is radian. So in a rotational motion, we have initial angular velocity. If it is scalar quantity, then we call it as angular speed. So the symbol is omega, and the unit is radian per second. Okay, so we have the final angular velocity. To differentiate initial and the final, so initial usually we use a knot to represent the initial angular velocity. For the final angular velocity, we just simply use omega, just omega, and the unit also radian per second. However, for acceleration, so in a rotational motion, we call it as angular acceleration, which has the symbol of alpha, and the SI unit is radian per second square. These are the terms that we use in rotational motion. And the velocity actually is v is equal to delta s over delta t. So same as the final angular velocity. So instead of omega, the omega can be defined as delta theta divided by delta t. Okay, where delta theta is called it as angular displacement, t is time. So however, for linear acceleration, right, or for the acceleration, a is defined as a change of velocity to the change of time. For angular acceleration, we can define the angular acceleration as the change of angular velocity to the time. You can always make a comparison between these two. Translational motion and rotational motion. The kinematic equation that you learned before this, first one is v equal to u plus at. Okay, then we have delta s equal to ut plus half at squared. Then we will have v squared equal to u squared plus 2a delta s. Then eventually we also have delta s is equal to u plus v divided by 2 multiplied with t. Okay, we can also have the similar kinematic equation applied on rotational motion. So in the rotational motion, we will have omega equal to omega naught plus alpha t. Then delta s is equal to ut plus half at squared. In a rotational motion, the kinematic equation is delta theta is equal to omega naught t plus half alpha t squared. In rotational motion will be final angular velocity of omega squared equal to omega naught squared plus 2 alpha delta theta. Right, so lastly will be, so delta theta is equal to omega naught plus omega over 2 multiplied with t. So you can see that, whatever concepts that I use in a linear motion can be applied in a rotational motion. But it's just change only. So instead of the linear speed, I change to angular speed. So instead of linear acceleration, or we call it as acceleration, you can change it to angular acceleration. In a linear motion, usually, for example, in 2 dimensions, to the right as we take it as positive x, then pointed upward is positive y. This is a normal sign convention for a linear motion. So rotational motion, it is rotating, so there's no x and y, right? Rotating, it can be either rotate in clockwise or anti-clockwise, correct? Because it is rotating. So usually the normal sign convention that we're using is if clockwise direction, this is clockwise, negative, right? If it is anti-clockwise, anti-clockwise means counterclockwise direction, positive. That is the normal sign convention that we are using. And sometimes this omega, so omega here I written here, the SI unit is radian per second, but sometimes the unit will not state in unit radian per second. So sometimes will be given in revolution, right? Or even in this, it will be given in revolution. One revolution is actually equal to 360 degree, which is equal to 2 pi radian. That is one revolution. So if I want to convert from one revolution to radian, you have to multiply with 2 pi. Okay, now, so we know that there are a lot of analogy between the linear terms and the angular and the rotational motion. So any relation between the V and omega, or any relation between the angular displacement and the linear displacement, yes, it can be related to one another. Okay, actually, delta S is linear displacement, is analogy with delta theta. And in a linear motion, we have the speed. It's analogy with omega in rotational motion, acceleration, analogy with angular acceleration in a rotational motion. So they are actually close related to one another, where delta S is equal to R delta theta. V is equal to R omega. A is equal to R alpha. So we just add additional R there to relate them together. Okay, this is a relation between the linear and the angular parameter. Let's say this is my circle, and the radius of the circle is R. Delta theta is here, so I would like to know that what is the displacement. So we know that delta S is actually R multiplied with delta theta. This linear parameter, we call it as linear speed. So sometimes we also call it as tangential speed. This one you can call it as linear speed or tangential speed. Okay, so same as the acceleration. So this acceleration, you can call it as linear acceleration, or you can also call it as tangential acceleration. Now next is torque. Torque, you can imagine it as rotational force. In a linear motion, we have force, right? So, but in a rotational motion, we don't call it as force, we call it as torque. Okay, and what is torque actually? Torque is actually the tendency of a force to rotate an object. Force, we use a symbol of capital letter of F to represent it. So torque, we use a symbol of tau. This one read as tau. Tau is a vector quantity. It is defined as R crossed with F. Right? This R is called it as lever arm. F, of course, is the force. That's a definition of torque. So this is a cross product between two vectors. So torque is actually same as RF sine theta, where theta is the angle between R and F, right? Okay, so for example, this is my wrench, and I'm applying the force in this direction, and this is the force. The length of the wrench is R, and the direction of the force that I apply compared with R is theta. So from here, you can actually find out what is the torque applied to the wrench, because by definition, torque is RF sine theta. How can you increase the torque? You can either increase the force or increase the R, which is the lever arm. Here is actually the axis of rotation. For example, this is the door of a room. Why the knob installed at the end here and you don't install the knob at the center? When you open the door, actually there's a rotational motion, right? You open it like this, rotate, and this is the axis of rotation. This is the hinge of the door. Okay, why you want to install the knob of the door at the end and not at the center or here? So if you put it here, definitely you cannot open the door, right? So if you put it here, yes, you can open the door, but maybe you can, it depends on what is the weight of this door. So, but if you put it here at the end here, basically you already increase the lever arm, okay, because you're applying the force in this direction, and the lever arm is here. This here is the axis of rotation, and that's why it's easier for you to open the door. Torque is defined as lever arm crossed with F. So lever arm is basically the length. The unit for lever arm is meter. The unit for force is Newton, and therefore SI unit for torque is actually Newton meter. Torque is a vector quantity. So torque is the force that causes the rotational motion to happen. So positive torque means is anti-clockwise direction or counterclockwise. Negative torque means is clockwise direction. And if we have more than one force tends to rotate the object, for example, you have the seesaw here, and the fulcrum of the seesaw is maybe is here, and there are two persons sitting on the seesaw. Okay, basically two forces acting on the plank of the seesaw. Okay, where are the two forces? Gravitational force on the first kids. So gravitational force is M1G. Person number 2, there's another gravitational force, M2G. And I like to get what is the net torque produced. So net torque produced will be equal to torque due to the force 1 plus torque due to the force 2 plus, if you have more than 2, they have torque 3 and so on. So you have to consider what is the sign convention for each of the torque. Okay, for example, this is a seesaw and the axis of rotation is here. Axis of rotation. Now you just imagine that kids 1 is sitting at the end of the plank at a distance of R1 from the fulcrum or from the axis of rotation. Okay, what is the torque produced by kids number 1? Okay, I call out my ruler. Okay, for example, this is my ruler. This is a gravitational force applied this direction. So axis of rotation is at point O. Okay, maybe I move a little bit. Okay, point O, and you're applying the force at this point. The direction of the force they apply is directed downward. The ruler will tend to rotate in this direction, right? So initially it's like this horizontal, now rotate is in this direction. Okay, what is this direction? It is clockwise or anti-clockwise? Anti-clockwise, yes, very good. So anti-clockwise means the torque produced by force 1, by M1G. Force 1 is, so torque 1 produced is plus M1G multiplied with R1. The angle between R1 and M1G is 90 degrees. Sine 90 is equal to 1. Right, so that's why I ignore the data. Okay, plus torque 2. Torque 2 is torque produced due to kids number 2. So kid number 2 has a gravitational force of M2G. Similarly, I have also axis of rotation is here at 0 here. Now I'm applying the force at this direction. So what happened to the ruler or to the plank? It will tend to rotate here. This round here, M2 will be rotated in clockwise direction. So clockwise direction means the torque produced is negative. So plus negative R2 M2G. So R2 is actually from the axis of rotation to the force. The force is M2G. So it's negative because this force tends to rotate the plank in the anti-clockwise direction. So what is the angle? This is 90 degrees. Angle between the R and the F is 90 degrees. Sine 90 is equal to 1. And that's how you get the net torque. So we have a condition at equilibrium. So in a linear motion, whenever you see the word of equilibrium, then we will say that, okay, summation of the net force is equal to 0. So that is one of the conditions or the first condition of equilibrium. So there's another condition for the equilibrium is summation of torque is also equal to 0. So this one is the first condition of equilibrium. This one will be the second condition of equilibrium.